In nuclear physics, the island of stability is the prediction that a set of heavy isotopes with a near-magic number of protons and neutrons will temporarily reverse the trend of decreasing stability in elements heavier than uranium. Although predictions of the exact location differ somewhat, Klaus Blaum expects the island of stability to occur in the region near the isotope 300 UBN. Estimates about the amount of stability on the island are usually around a half-life of minutes or days, with some optimists expecting half-lives of millions of years. Although the theory has existed since the 1960s, the existence of such super-heavy, relatively stable isotopes has not been demonstrated. Like the rest of the super-heavy elements, the isotopes on the island of stability have never been found in nature, and so must be created in an artificial nuclear reaction to be studied. However, scientists have not found a way to carry out such a reaction. Theory and origin. One fact should be emphasized from the outset. While the various theoretical predictions about the super-heavy nuclei differ as to the expected half-lives and regions of stability, all theoretical predictions are in agreement. Super-heavy nuclei can exist. Thus, the search for super-heavy nuclei remains as a unique, rigorous test of the predictive power of modern theories of the structure of nuclei. Seaborg and Loveland, 1987. The possibility of an island of stability was first proposed by Glenn T. Seaborg in the late 1960s. The hypothesis is based upon the nuclear shell model, which implies that the atomic nucleus is built up in shells in a manner similar to the structure of the much larger electron shells in atoms. In both cases, shells are just groups of quantum energy levels that are relatively close to each other. Energy levels from quantum states in two different shells will be separated by a relatively large energy gap. So when the number of neutrons and protons completely fills the energy levels of a given shell in the nucleus, the binding energy per nucleon will reach a local maximum, and thus that particular configuration will have a longer lifetime than nearby isotopes that do not possess filled shells. A filled shell would have magic numbers of neutrons and protons. One possible magic number of neutrons for spherical nuclei is 184, and some possible matching proton numbers are 114, 120 and 126, which would mean that the most stable spherical isotopes would be FLEROVIUM-298, UNBINILIUM-304 and UNBIHEXIUM-310. Of particular note is UBH-310, which would be doubly magic, and thus the most likely to have a very long half-life. Recent research indicates that large nuclei are deformed, causing magic numbers to shift. Hassium-270 is now believed to be a doubly magic deformed nucleus, with deformed magic numbers chapter 108 and 162. It has a half-life of 3.6 seconds. Isotopes have been produced with enough protons to plant them upon an island of stability, but with too few neutrons to even place them upon the island's outer shores. It is possible that these elements possess unusual chemical properties and, if they have isotopes with adequate lifespans, would be available for various practical applications. In particular, the very small critical masses of transplutonic elements implies that if stable elements could be found, they would enable small and compact nuclear bombs either directly or by serving as primaries to help ignite fission-fusion secondaries. This possibility motivated much of the early research and multiple nuclear tests by the United States and the Soviet Union aimed at producing such elements. Half-lives of the highest numbered elements. All elements with an atomic number above 82 are unstable, and the stability of elements generally decreases with rising atomic numbers from the relatively stable uranium upwards to the heaviest known element. 118. The longest-lived observed isotopes of each of the heaviest elements are shown in the following table, discovered thus far. This makes it seem likely that there are long-lived undiscovered isotopes among the even heavier ones. For comparison, the shortest-lived element with atomic number below 100 is francium with a half-life of 22 minutes. The half-lives of nuclei in the island of stability itself are unknown since none of the isotopes that would be on the island have been observed. Many physicists think they are relatively short, on the order of minutes or days. Some theoretical calculations indicate that their half-lives may be long, on the order of 109 years. The alpha decay half-lives of 1700 nuclei with 100 Z130 have been calculated in a quantum tunneling model with both experimental and theoretical alpha decay Q values. The theoretical calculations are in good agreement with the available experimental data. A possible stronger decay mode for the heaviest superheavies was shown to be cluster decay by Doran N. Pinaru, R.A. Gergescu, and Walter Greiner. Islands of relative stability. Even bismuth was found to be slightly unstable in 2003, with an alpha emission half-life of 70191900000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 beyond bismuth have relatively or very unstable isotopes. Astatine, radon, and francium are extremely short-lived. Even thorium, with the largest known half-life in this region, is still about 1 billion times shorter than 209 Bi. So the main periodic table ends there. By geographical analogy, bismuth is the shore edge of a continent. A continental shelf continues though, with shallows beginning at radium that rapidly drop off again after californium. Significant islands appear at thorium and uranium, and with minor ones form an archipelago. All of this is surrounded by a sea of instability. Current theoretical investigation indicates that in the region Z equals 106 to 108 and N 160 to 164, a small island peninsula might be stable with respect to fission and beta decay, such superheavy nuclei undergoing only alpha decay. Also, 298 FL is not the center of the magic island as predicted earlier. On the contrary, the nucleus with Z equals 110, N equals 183 appears to be near the center of a possible magic island. In the N162 region, the beta-stable fission survived 268 Sg is predicted to have alpha decay half-life tilde 3.2 hours that is greater than that of the deformed doubly magic 270 Hs. The superheavy nucleus 268 Sg has not been produced in the laboratory as yet. For superheavy nuclei with Z greater than 116 and N 184, the alpha decay half-lives are predicted to be less than 1 second. The nuclei with Z equals 120, 124, 126 and N equals 184 are predicted to form spherical doubly magic nuclei and be stable with respect to fission. Calculations in a quantum tunneling model show that such superheavy nuclei would undergo alpha decay within microseconds or less. Synthesis problems. The manufacture of nuclei on the island of stability proves to be very difficult because the nuclei available as starting materials do not deliver the necessary sum of neutrons for the synthesis of isotope 298 of flerovium. These and heavier isotopes are not available in measurable quantities, making production virtually impossible with current methods. The same problem exists for the other possible combinations of isotopes needed to generate elements on the island using target projectile methods. It may be possible to generate the isotope 298 of flerovium, if the multi-nucleon transfer reactions would work in low-energy collisions of actinide nuclei. One of these reactions may be 248 cm plus 238 U 298 Fl plus 186 W plus 210 N. Hypothetical second island. At the 235th National Meeting of the American Chemical Society in 2008, the idea of a second island of stability was presented by Yuri Oganessian. This new island would be centered on element 164, especially the isotope 482 UHQ, with a stability similar to that of flerovium. It is thought that to be able to synthesize these elements, a new, stronger particle accelerator would be needed.